So today we're going to talk a little bit about the towards safe learning and perception-based network computing systems. And I'm going to introduce a little bit about how we can solve those problems with a risk-aware approach. So in our nature and in our world, unfortunately, everything that we see are some kind of stochastic. Either from pollen to the stock market, there is basically no way that we can exactly know what is going to happen in the future. And for most of the cases, human has learned to survive with those kind of uncertain environments, but it's still too dangerous and costly. Whenever something happens, we send a human officer in there. So what are the potential remedies that we can do? We can somehow send a robot instead, right? So it's less costly and less dangerous for human for robots to operate in those environments. But however, it's not an easy job to do. So first of all, there are very limited communication between human and the operator and the robots. And the environment that robots are sent into, so something after a disaster, is going to be very uncertain and it's going to be potentially adversarial. And robots must make its own decision, planning and control in those very highly uncertain and potentially dangerous environments. However, as a human by ourselves, we somehow learn how to adapt to those uncertain environments through our experiences. And it is not very hard to transfer from one experience to another by just teaching and even talking. But however, our transfer of knowledge from human to human is going to be extremely difficult for robot to understand. And most of the time, it's going to confuse the robot. So what we have in hand as a human in terms of those uncertain environments, we have extensive experience on how we can adapt to those dynamically changing and potentially dangerous environment. And here's the gap. What robots want is a bunch of 1 and 0s and basically code that they can operate on. Or is there something in between? Yes. So something that is comprehensible in mathematics. So we know how to convert a mathematical equation into the code that robots can operate on. So then there's going to be our major task, or the three parts of the task. First of all, what we have in hand is shown over here. We do have the understanding of the dynamic, uncertain, and potentially dangerous environment. And we do have, as a human, have the methodology of make a safe decision and planning and control. And there's the first thing that we need to do is we need to build a bridge from all of these that we have in hand to the comprehensible mathematical equations. And we're going to grab some of the grad students that are going to help us to write a code that the robot can understand, which is building another bridge. And potentially in the larger application or deployment of the task, we have to teach not only one, but a network connected, a team of robots, confused robots. So in today's talk, we're not going to talk about the error bridge, but we're going to talk more about the first bridge. So how we can build the first bridge, that the approach that we take is called a risk-aware approach, which basically we're highlighting the safety, then we can easily convert all those concepts into a comprehensible mathematical equations. So today's talk is going to be majorly divided into three parts. And in the first part, we're going to talk about how we can actually see the impact of uncertainty in a very nicely assumed linear network control systems. And then we take one step further. We drop the assumption that we have the exact distribution or statistics of the noise, and we see how that is going to affect our entire system. And in the last stage, we're getting closer to reality. We're going to drop the nice assumption that we actually know our system, and which is basically seeing how the uncertainty is going to impact in a perception-based system. So in the first section of our talk, we're going to look at a very special category of the network control systems, which is a consensus network, with the objective trying to reach a consensus among all agents or components of the network. So in those consensus networks, we highlight three very commonly used consensus networks. One is called random, which is basically have a bunch of agents trying to meet up or trying to get together at the same location, at the same point, at the same time, which is what we're doing right now today. Or is car platooning. If in your everyday driving, you can see all the cars on the highway trying to form a platoon and trying to cooperate with each other to reach the destination. Or there's how to use the secondary system is called power grid-based synchronization. You have different generators in the power grid. They're trying to synchronize their phase in terms of generating power, and this can also be controlled by very nicely secondary systems. In today's talk, we're going to highlight heavily on this car platooning problem. And talking about car platooning, what is hard about it? If everything is perfect in the car platooning, there is nothing hard. We can easily predict what is the exact state in the future of systems. And the task is going to be extremely easy. But however, something is going to be not a perfect. We consider two major of imperfections of the platooning system, which one is the input uncertainty. Imagine yourself driving a highway, even though you're trying to hold your foot and try to maintain a certain amount of the gas pedal, but your foot is actually shaking all the time, and then your input is going to be uncertain. As a human or as a best elite robot or even a computer that we have in here, we also experience time delays. No matter something happens, take time to process all those new signals and new changes in the environment, and then we can make it reactions. So we'll consider two major of the imperfection as the input uncertainty, which is the noise, and also time delay, which is how the time that it take to react to any of the changes of the system.
Input, you mean measurement or gas pedal?
Gas pedal, input which is actuator. So yes, it's directly applied on the U vector.
So this is imperfection on the dynamics, not on the measurement.
Not on the measurement, but it can be induced by the measurement. Since your measurements are, if you have a measurement feedback control input, then if your measurement is noisy, then your input is going to be noisy as well. If it's a linear function of your measurements, for example.
The U is a function of the measurement.
Yes, for example. Yeah. It's going to be induced by that, but we categorize it into one big category is saying that it's going to be input uncertainty. It's going to directly affect on your U vector.
But why don't you call it dynamics uncertainty?
Yeah, we can. Yeah, that's a good point. So we can the dynamic uncertainty in general will say that it could be uncertainty in your different level of system. It could be uncertainty in your dynamics itself. But here we just highlighted on that it's going to be origin from just the input that you put into your control system. Only be affected on the U vector, but nowhere else. We're going to see this effect into how we design the feedback controller. All right, so given these uncertainties, we're going to see the chances of having the inter-vehicle collision. So nothing can be as perfect as that can be done over there. So we'll need to consider a collision system. So first of all, let's build up the model that we have to form a platoon. So the major objective of forming a platoon in the highway is going to be have a constant inter-vehicle distance, which means that if you're trying to follow another car, you're trying to keep your distance as a time variable, which is not changing over time. And for all the cars, they're trying to reach a same velocity. So we're trying to platoon as an entire team. So in order to achieve that, we're going to consider a second order model, which is saying that your position of the vehicle is going to be the differentiation of your position is going to be given by the velocity. And then your derivative of your velocity is going to be given by your control input, which is the acceleration. And you have noise over your control input, which is over there. And for each of the vehicle, this is for each of the independent vehicle. And the feedback that we can see over here is given for each of the independent vehicle is going to give by two terms. So one term is going to find the mismatch between the pairwise velocity differences. Since our objective is trying to minimize the, in the statistics, that the difference between each of the vehicles, and also the platoon distance is second term. And the Kij over here, you see, is going to be the feedback gain, and it's going to eventually show up in your communication network. And there's one more important thing over here, that you can see the vector from the feedback that we had has the t minus tau, which means that which denotes the time delay. So for whatever measurements or the communication they have from other vehicles, you're going to experience a positive tau steps of time delay that you can wait. You need to wait for tau times, then you can apply to your control input. And the beta term over here is going to balance the importance between either of the feedback from the position and feedback from the velocity. And if we have all these vehicles all together, we put them into one large long vector, we can form a compact dynamics, which is given by this second order dynamic over here. And one more important thing over here is this L matrix is going to be your graph Laplacian. And it's basically the graph that is constructed by each of these KIJs you're feedbacking. And in there, how we can know if it's going to converge? So it's not going to converge to a steady state or form platoon for any of the graphs or any of the time delays. We have to show that for a certain graph that is select and with a certain number of time delay, the pair of the time delay and the eigenvalues of your graph selection over here has to be land inside of this small subregion S. If you have a pair that is land inside of there, then your platoon is going to converge to the steady state, which is basically you have a Platon distance of each of the Platon distance is going to be a component of the R vector up there. And then since we reach a steady state, and we're going to solve this stochastic delay differential equation, and we're trying to find the edge to norm of the system. We know that the output of the system or the observable of the system is going to be the intervehicle distances. That is what we care about. It's going to have a mean of this constant value R, because we're trying to have them to plateau with the fixed distance, and the variance is going to be this term. And this term does not look like that nice, but you can see some parts in here. So this is the highest. This is going to be the ith basis of the Euclidean space. And these two terms, the E of I plus 1 minus E of I, is going to give you the distance between the vehicle I plus 1 and I. And this f function is going to be the integral. And that integral is basically from the integral trying to put over the transfer function to get the H2. And we can see over here, the G of square is going to be the noise magnitude of your noise, of your added diffraction noise. And this tau is going to be time delay. And this Qj is actually the J's eigenvector from your graph calculation. So from all that, we know that the intervehicle distance between each of the vehicle is going to be a random variable. And from probability 101, we know that if something is going to be a random variable, it's actually a normal random variable. If something is going to be a normal random variable, it means that the collision, or the cases that is going to be less than 0, is eventually going to happen. So no matter how well designed your network and how well designed your platoon, you're eventually going to encounter a collision in your system. And imagine how many times you can see a car accident on the highway, and when that happens, it's not just for two cars. It's going to cascade. It's going to affect more components in the system, and we would very like to see how these kind of uncertainties or how this kind of failures is going to propagate in our secondary consensus network. So that's why we have two concepts in mind. One is cascading space, and one is cascading time. So cascading space is very common that we see. It's saying that if some part of the system starts to initiate a failure, and if that, how or if that failure is going to propagate through the network and reduce and cause the other parts of the network into another failure, or cascading time. If I make a wrong decision at the current time, if I'm going to affect my state in the future. So the way we quantify or define the cascading failure is going to take in, it's going to be looking at the conditional distribution of the random variable. The random variable d of j is going to be the distance of the pair or the vehicle that we're interested in, and it's going to be conditioned on different conditions, conditioned on different events. One is something goes to be the collision. We're going to assume some other pairs are going to have a distance exactly equal to 0. That means that it has a collision already. Or it's going to be a very near collision situations. Or we just simply take a snapshot of the plateau and we provide some measurements to the system. It's also going to help us to identify how the pair at J, instead of the other pairs, is going to react to the existing measurements or existing failures.
Guangyi, can I ask a question?
Yes, go ahead.
So am I right in understanding that all of your modeling is going to assume that you have this kind of proportional control operating on each vehicle on this constant distance and constant and same velocity objective that you showed on the slide? Yes, the slide. So this is so you're not going to talk about kind of an alternative control scheme, but instead be analyzing what happens under this fixed control scheme. Is that right?
All right, exactly. So we're going to fix our feedback control, and we're trying to see that how the graph is going to play a role in this kind of feedback control.
Got you. And is there a reason to assume that this kind of proportional feedback control is a good model? It feels like intuitively we should care. For example, sorry if I can annotate. I'm not sure if you can see what I'm annotating, but like this term, for example, here seems to care identically about whether you are closer than the expected distance or whether you are farther than the expected distance. But you would imagine that an actual controller that somebody would design for this problem would care much more about if you're closer than if you're farther away, right? So it feels like, yeah.
Right. You are exactly on point. So we consider this is very close to realistic is, first of all, a second order system. So it's very similar to the everyday driving scenarios that you only have the control over your acceleration. And also, this feedback control law is we obtain it actually from the control objective that we see over here. Is we have two major objectives. One is we're trying to have all the cars traveling the same velocity, and another one is trying to have all the other cars trying to maintain their interval distance. However, it does not have to be identical, but as long as we have a certain target in mind, we can just put them into the feedback control law, and then they will form the consensus in the steady state.
Yeah, and there's no notion of safety. I guess like another way of asking my question is to say we are stating these objectives, but not really stating any notion of safe states or any notion of unsafe. Yeah, we're not really explaining anything at all in the controller synthesis process, right? We're just saying we want to ideally be somewhere in the neighborhood of constant inter-vehicle distance. Okay, yeah, thanks.
But sure. But we're going to cover safety in the very next slide.
Okay, yeah.
So we know this, and we haven't formally defined what is of the safe and what is not safe, or how we can evaluate what is the chance of collision in this kind of systems. So the intuitive way of quantifying the chance of collision is basically just, since we have a 1D normal random variable, right? Then we can just put a probability measure on that. See what is probability of your distance, since it's supported on real, and what is the chance of the distance less than 0. That is very intuitive. Or you can use some concepts that you can borrow from the finance community. It's called value risk. It's basically saying that with certain confidence level, say this epsilon over there, and what is the distance, or with this kind of probability, what is the distance such that most of the outcome of my random variable is going to be safe. So both of the two they quantify the same concept. So the probability is over here, and you can see that it's basically measuring the integral of your density function whenever it's less than 0. But however, the value risk is saying that if your density function, so whenever your density function, the integral of density function is exactly at epsilon, what value is going to be that, and that will be called value risk. So both of terms is going to give you a very basic sense of how dangerous or how likely something is going to happen. But there are certain shortcomings. So if your density function actually changes, but their integral up to a certain point is going to still be the same. So the probability and the value risk is going to give you the exact same output. But however, in terms of the collision, these two are totally two different scenarios. One is going to exactly a more severe collision, and this one over here basically indicating a very small bound. So we need to find a way to differentiate one from another. And that's why we use the very commonly used concept called the average value risk or conditional value risk. This is going to incorporate the tail behavior of your existing distribution, and it's saying that what is the expected outcome of my random variable whenever my random variable is below or upper, either way in the worst case of scenario of the value risk. It's basically saying that if I'm in these very bad situations, what is the expected outcome of myself in those regions? So if we use the average value risk, this one and that one, two different density functions is going to give us a different outcome in terms of A bar. And then we'll be able to capture what is the tail behavior of this random variable. So we have the value risk in hand. But as a human, what does it mean to us in terms of safety? Average value risk in hand is basically going to give us a value between -infinity to infinity. And what does it mean to us? And what does it mean to the collision? So first of all, we for sure does not want collision to happen. And that's why, as human or as a robot, we're trying to build an alarm zone. We're trying to see, with this kind of random variable in hand, how far and from the doom state or the states that I do not want to enter, which is whenever the distance is less than 0, we want to build an alarm zone around these zeros. Say for example, if we have something is a safe distance that I consider. So if my average value risk is even further than the safe distance, I'm going to be safe, which is very common as a human. We consider something to be extremely safe, or something is going to be extremely dangerous. So we use this aggregate shape of the level sets to cover all the potential existence of this random variable in 1D, and we convert the real value average value risk, which is spanned between minus infinity to infinity, into something using this function C of delta here, into something parameterized, into something that we can comprehend. So we basically map all these values in the real into the half of real, saying that we find another value by solving this optimization problem. It's going to give us value between 0 and infinity. 0 means we'll be safe. Your average value risk is going to be on the right-hand side of this ROC, which is something we consider to be a safe platonic distance. Or you're extremely dangerous and nobody can save you. You are going to be exactly at 0 over here, or even beyond on the left-hand side. So with that all in mind, we still need to find what is a conditional distribution, right? So we have our risk measure now. We have our level set. We know how to interpret them, but how we can still find what is the cascading effect. So the cascading effect can be found by finding the conditional distribution on A and D real on the normal random variable, which is pretty intuitive. So for example, if you're interested in the vehicle and number 5, and this is own variance, and we know that some vision or some other bad thing can happen to vehicle 2 and 3, and also vehicle 7 to 9. We have to somehow truncate our covariance matrix by doing this, and we have to do some kind of the reformulation. And then whenever we have this truncated covariance matrix, we can find the conditional mean and the conditional variance of the vehicle number 5 by using the following equation. So all the green, blue, and red over here, you can find its correspondence in the truncated covariance matrix. And you can easily find this inverse of this sigma to the 2 over here, which is positive definite. With all this conditional, then by doing this, we can find the conditional mean and covariance for every pair of vehicles in the platonic system by using the statistics that we obtain from the H norm. After doing this, so we have all the necessary pieces in hand. So we have a risk measure defined like this. We have our conditional statistics of our random variable, which is on the existing conditions. Then we can compute our risk values. So this is the risk value we computed in terms of the level sets or alarm zones that we define, and it has 3 interesting branches. All these 3 and why is the reason that it's going to give you 3 different branches? It's based on how severe or how badly your current situation of your conditional random variable is in. So for a certain confidence level, so as we recalling the value risk, so this kappa epsilon is going to be a function that is defined by the confidence level, and this is the inverse error function. This is basically going to tell you that, and most interesting, this is independent to any of your conditional mean and variance over there. This is going to tell you that with certain confidence level, if you have your certain conditional mean and variance, we're going to partition the entire real into 3 different parts. If this kappa epsilon, which is a function of the confidence level, is landing on this side, your risk is going to be 0, which is you're going to be extremely safe. Your AVAR is going to be the extremely right-hand side of your safe distance. Or if something in between, it's going to give you a value between 0 and infinity. It's going to quantify how dangerously you're going to have a cascading collision in your system. Or if your kappa epsilon is going to over here, it's going to say that you're in an extremely bad state and the collision is very, 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 very likely going to happen. And in those cases,
so this is likely or certain to happen the infinity?
Oh, it's going to be certain. And it's going to be certain in terms of confidence level. So we can say that the collision is for sure going to happen with 95%, for example, with 95% confidence level. For 95% of the case, your collision is going to happen in terms of average values. And we can see that we know that this is not a function of your conditional statistics, right? But and what is going to change in here? So if I change our design of network, or if I change a different system, something that's going to is not this couple over here, but we're going to change where we're going to partition these 3 different atoms. So you can see how the conditional distribution is going to affect the risk level in here. And quantifying the risk. So here's basically quantification of the risk. And quantifying the risk is kind of straightforward since with the formula that we get from the previous slides. And there are a few interesting things in here. So the red dots over here denotes it whenever the vehicle has already experienced a collision, and we consider a platform of 20 vehicles in here. And this dashed line over here is considered the risk of having the first collision before any existing collisions. And you can see that how the network reacts when the collision exaggerates, or where there's more failures introduced to the systems. If you have a one cyclic graph, it's a graph that is a form of cycle, or five cyclic graph, which is the graph form of cycle, but you look at 5 years neighbor, or you have a complete graph. You can see that if you have a complete graph, even though no matter how many new failures have been introduced into the systems, your risk of having the cascading collisions is going to remain the same. It's not going to make your system worse than the previous behavior. But if you have a cyclic graph or 5 cyclic graph, you can see for some certain pairs of vehicles, your risk is going to shoot up and eventually be infinity. This is going to give some insights into the designing stage of your network control systems. So which graph should I use or should I consider such that I can make designed network control system is going to be robust against cascading failures. So not only one failure, but more failures in the future. And as I mentioned earlier, quantifying the risk is kind of straightforward and is not a really hard job to do. But we have to ask the question is now what? So can I know that if I can design a good enough network or good enough control system that it's going to be have my risk minimized to 0 and going to be safe against all type of failures? The question is probably not. The first question we have is if I give you a design target, saying that I want my risk of cascading failure of the entire network to be below certain threshold, can I do that? So the question is, can I change my input time delay? Probably not. It's a hardware level, and it's extremely hard to minimize. And can I change my noise level? It's extremely hard in terms of engineering. We have to do a lot of other experiments to try to reduce the overall uncertainty. But there's certainly one thing that we can change. It's going to be our graph structure in the network control system. And the question is there going to be the limit if I play with all the potential stable graph structures? The short answer is yes, but it's hard to find. The major reason is that since we're looking at the cascading collision and we need to look at the off-diagonal elements of the coherence matrix, and their signs are not really well behaved. And so, for example, this is the big sigma matrix of the complete 1 cycle and 2 cycle graphs, and they can be either positive or negative. And over there, it's going to be extremely hard to find the boundedness of the entire coherence matrix. So we'll have to find another way around. So what I did is that we tried to rewrite these not very nice expression that we have from the H2 into a trace of two different diagonal matrices. And since one of the matrices is going to be a normal matrix, and we're going to apply some results from 90s, saying that we can actually bound the trace of this product of these two matrices by their eigenvalues. So one is the summation of their eigenvalue product of their eigenvalues in the non-descending order, and the other one is going to be the same eigenvalue, but the other one is going to be the flipped order over there. Then by doing that, we can somehow sandwich this not well behaved coherence matrix like that. Then we can have the boundedness of each of the terms of the coherence matrix. Since we have a bounding of the coherence matrix terms, then our risk function is basically a function of each of the coherence terms. Then we're looking into the risk values. However, the risk function itself is still not well behaved. Why? All the terms from the coherence matrices are actually coupled through the graph. And it's extremely hard for us to define what are the feasibility set of the alternative one. Since if you want to minimize the risk is going to show up in the cost function. And what are the constraints? The constraint is simply what we're saying that they are from the graph. And this is hard to solve. So we take one small step back. We just inflated all the field evolution, which is saying that we're going to use all the upper and lower bound that we have for the conventional terms and trying to inflate the entire feasibility set with a cube in R3. Then by doing that, we are lucky enough to show the risk function in S is either monotone or convex over this inflated region, then it's straightforward to obtain an upper and lower bound for the risk factors. For that, we'll be able to easily quantify what is the feasibility of your design target. If somebody comes to you saying that, okay, can I use this exact dynamics and design target that has a risk threshold is going to be below certain things? You can directly go and find this lower bound, say yes or no. You don't have to go over and test all the potential combination of the graph structures that can be used, but directly using this result and go there and tell them yes, answer this yes or no question. And since it will be a little bit nicer, this is somehow conservative, but since it can be a little bit nicer, if you have a broad range of graph structures, say for example, if you have an all-to-all connected graph, but I'm allowed to change weights, we can give extremely close bounds, upper and lower bounds on how your risk value is going to behave. It's going to change with that certain range. So with that, we're going to take a little bit summary of the section number 1. We have enough time. So basically, there are a few technical metrics or derivatives that we obtain from this from this very nice research work. Is that if you want to drive safely, there are a few important tips. First of all, is keep a safe platooning distance. As you know that your platooning is going to be a random variable with the mean of the platooning distance and covariance, right? So if you enlarge your mean, your risk is going to be linear function of your mean is going to linear decrease with the increase of your mean. And always also stay focused all the time. We're going to reduce your time delay, and you know that it's going to have negative impact on your overall risk. And also see through more than one car. That is another interesting point. We show that if we increase the connectivity of the network a little bit, your risk is actually going to decrease over time. So that is the very first part. And then we're going to drop the very nice assumption that our additive noise to the system is going to be constant. We're going to get closer to reality. So we do have platooning, but the thing that if something happens, the driver is going to react with panic, and their behavior is probably going to change. And the question is, what if the distribution of the noise changes and can we still achieve the same goal? The short answer is no, we cannot do that. So we're going to face a problem of having the uncertainty or the ambiguity of the uncertainty. So uncertainty itself is saying that we do not know where exactly our random variable is landing on this spot, right? But we're now looking at the higher level problem of having the uncertainty of the uncertainty, which means that we do not know where it's going to land, but we do not know which distribution it's going to follow. So in order to incorporate this kind of or mitigate this kind of challenges, there are two different approaches. One is, of course, get better estimation. So trying to get to the ground truth distribution of your noise, or be more conservative. So in this work, we'll consider the problem of being more conservative, which is saying that we'll have to design a feedback controller that is going to be robust against all potential distributions that is around my gas, this black P over here, and such that I'm trying to hope I can, for all of them, I'm going to incorporate the actual ground truth distribution in my ambiguous set, which is the box shape that I draw over here. It's because then if you see a drunk person walking on the street, you're not going to try to predict his action in the future, but you want to be more conservative, try to get to the other side of the street and try to not just walk by him and say that, okay, I know how he's going to react. So we're going to still consider a very similar problem and with very similar linear time invariant system. And over here, we'll have our states is again by the position of the vehicles. And the control input is going to be directly applied on states in this time. And most importantly, what is interesting here is that this omega t over here, not like what we have previously as a Gaussian random variable. This one is going to be unknown. We're going to assume that it follows a unknown probability distribution that we have no idea what is going to be. So we're going to look at the problem of whenever some collision or some bad event happening in the plateau, we're trying to reform plateau and get back to the normal operating stage. That's why we want to consider a model predictive control problem. And in here, we're not only considering the unknown noise, we're going to also consider a certain amount of the input time delay, which is given by this ut minus tau. We're saying that no matter what command you send, excuse me, it's going to experience a tau time delay to be effective on the system. So we form our problem very nicely into a compact form, as a very classical MPC problem is going to do. And we have our y denotes all our initial conditions plus our future states of the system. And this is going to be our collected noise from time 1 to all the capital time t that we try to plan into the future. So we're going to write everything very nicely in this compact form, and we'll have a problem. So trying to reform a Plateau, and this c over here is a cost function that trying to measure how far we're deviating from our target Platonic distance. And we have two major constraints. We're trying to ensure their safety. One is cascading time, another one is cascading space. So cascading time is saying that I know that something happened at the t0, and I want to solve a optimal control problem such that this kind of failures or close failure situations will not get worse into the future in terms of the average value risk that we are all familiar with. Or cascading space. I do not want, when I'm trying to solve this optimal control problem, I do not want the other state of systems getting into a dangerous state because the existence of my initial failure conditions. So put everything in one nice empty problem, and this looks pretty easy to solve, right? But whenever I give this to one of the grad students and they the problem, they will ask a question. I do not know this actually. I do not know the probability distribution. So what do I do? The best thing that we can do is going to be my favorite metaphor. Is go to a Born error condition, Born error test. That's saying that if I'm trying to shoot, arrow to the target in a windy condition, but I do not know what is the distribution of the wind. So there's something I can do. The quick answer is yes. I can do tempo n number of testing, which is saying that I do aim at target at windy condition. I shoot a huge amount of arrows in there. I know my dynamics of the bow and arrow. I know it's going to land whenever there's no wind. I can also take measurements of where it's landed near target. If I subtract, since the linear system, if I subtract this, what I measured from what I predicted, I can actually get an empirical distribution of the noise, of the wind. Then I know the wind. So for the future practice, if I'm going to shoot target for the competition, I can actually apply the empirical distribution of the wind into my prediction of the future states. Then I can somehow predict if I still doing the same motion and with the same noise, how my arrow is going to land near the target. And that's how we call it using the sample average approximation, how we get the empirical distribution of the output of the system. Then by doing that, we have a very good guess of what is the actual noise is going to be, but there's still a question mark. How far is it from the true distribution? So this question is answered by using the following quantity. So we're not talking about distance, we have to equip us with a metric space. And we have to have a metric. So the one-system distance is the perfect metric to measure what is the distance from one probability distribution into another probability distribution. So it does not have a very nice formula here, but to give you a conceptually clear understanding, for two normal distributions, we can easily measure the type 2 one-system distance by using their mean, trace of the covariance, and the product of the trace of the product of their covariances. So with all that, and with one more nicely assumption that our underlying unknown noise is going to be, vanish, the tail is going to vanish exponentially fast, then we can somehow quantify the probability of the actual noise is inside a certain region of our empirical probability distribution, or in other words, in terms of the what's thing distance. This is what's thing. The distance between these two probability distributions is going to be less than some given radius, and we equip this probability with certain confidence level. So this is going by applying the concentration inequality, we can actually get the condition that what this radius is going to be if you provide me the number of samples you collected from the experiments, which is this n over here, and your confidence level. So this basically in here we have three parts interacting with each other. If you want a better, closer radius, what you do is that you get more sample from the experiments, or you get a higher percentage of your confidence level. But however, this is a quantity that we can compute, but we don't actually use in practice. There is a very efficient algorithm that we can use in practice, get a good estimation of the W1, what's the standard distance of the radius over here. Then we'll then go and apply that in practice. But this one gives the guarantee that if you do this kind of sample average quantization approximation, I can give you the confidence level such that your actual distribution is not going to be too far away from your empirical distribution. Then what we have is, this is the optimal problem that we're trying to solve, is whenever we have the actual distribution. So instead of solving the problem just with the empirical, with no guarantee, but we're going to solve it a distribution robust problem, which is saying that we're going to consider worst case scenarios among all the potential probability distributions in the ambiguity set. And then we'll have the probability guarantee of with the confidence level at least epsilon. This one is going to be greater than equal to everything we have on the left-hand side. We're saying that if we solve that, we'll be safe in terms of the probability of at least epsilon. Then this is our finally distributed robot MPC problem. And we probably can solve it, right? It looks pretty easy, but again, it is not as intuitive because finding the soup over all potential probability distribution is not easy job. We cannot basically discretize the space of all probability distribution, right? It's going to be a semi-infinite dimensional problem. We cannot put it in the computer program. So what we have to do is that we have to convert this one into a problem that we can solve. So by putting some very nice assumption that your cost function, your constraint over here are actually piecewise applied assumptions, piecewise applied functions. Then we introduce some slack variable and find a strong duality. Then we can actually show that the dual problem, we can by finding the dual problem, we can actually show that the original semi-infinite dimensional problem can be written as a convex opposite problem, which is finding the correspondence over here, and over here. So instead of solving all this, we're trying to solve all the three parts that we've seen below over here. And we can find one major similarity in here is going to be these two actually shares a very close relation to each other, and that is because the AVR itself is indeed a expected value. It's a bit the same as your cost function over there. So we can actually see that how we can use that to solve the distributed robust optimal problem without knowing the actual noise. And this is how it reacts to the time delay. And we can see that we can actually incorporate the cascading collisions, which is the existing collision in the first stage, into the problem. And whenever we increase the severity of the existing failure, we're going to expect that the entire problem is going to fail, and there does not exist any feasible solutions. So let's give some other details. There's one major take-home message for this section. It's going to be there is a trade-off between the safety and performance of your system when you're trying to solve a distributed robust optimization problem. So if you want to incorporate more safety, then you're trying to get a more conservative solution, and you're eventually going to lose your performance in terms of reaching target or finish your task, or the other way around. You're trying to get very efficiently reaching target or finish your task, you're going to somehow sacrifice safety over here. And the last section, I know the time is limited, is a very nice collaboration with Guangyi and Costas. And here we look at the problem of the 3D sync construction. And here is the background of the NeRF. I probably don't have the network, but again, we're basically having some sample views given to us some kind of a sculpture, and the sculptor is trying to build us a very nice sculpture. Then we can get any of the novel view that for a given pose. So we look at basically the same problem, but in the robot setting. So we assume that robot has the initial understanding of the environment through that is trained with some of the sample views from the environment, and the robot is going to reconstruct an environment, but very, very noisy. And the robot has to make a plan with this noisy environment. So with limited training views and the very uncertain reconstruction problem, so the planning of the robots is going to be extremely unsafe. It can either overestimate or underestimate its potential risk of having the collision with the entire environment. So in that, we have to collect additional views get a better training, better training result. And there's going to be a major question of where shall we look at in the environment to collect the additional views, and among all the potential views that we can get, which one is the best? So to answer these questions, we have proposed a approach. Oh, let me skip a little bit over here. So this is basically that if we have the perceived environment in terms of 3D Gaussians, then we can actually use our very familiar risk values to measure what is the risk or chance of having a collision with the environment from each viewpoint of the robots. And with doing that, we're going to actively mask out our environment with different risk values, which is saying that if I'm experiencing a higher risk environment, I'm going to have a more focus on my surroundings. If I have a less risk of colliding with the environment, I'm going to have a less focus around my surroundings. And with that, we'll have a masked environment, and that is going to be task relevant, right? If we are trying to plan robots, have robots pre-planned in the past, then for each viewpoint on the past, we're going to find a masked environment compared to the original one. Then we're going to propose, rather propose some tentative views around that. And the next question, so this answers the where question, and this is the answer the which question. So which question is going to be answered by compute the expected information gain from when most work on the Fisher RF, which is saying that we're on the mask environment trying to find which one of the candidate poses is going to give us the most informative views of the mask environment among all the potential candidate views. So with that, we can actually see the difference in here. So this is the active view perception selection process. And we can see that with the mask environment, we're going to select the view that is going to give us more construction on the high risk area, which is related to the pre-planned task. And if we do not do that, you can see the difference over here. And this is on the left side is the initial understanding of the environment, and we're trying to build additional view among that. So just give a quick overview of the result. And this is a process of we're trying to do the masking based on different risk values along the pre-planned task. And you can see here, we can actually see the effectiveness of the risk-aware environment masking. We can certainly reduce the uncertainty of the understanding of the environment near the pre-planned robot task. And we can actually quantitatively analysis of that. We can have the quantitative analysis of that is we can actually compute what is the one-certain distance from my perceived environment, internal 3D Gaussians, to the ground truth. And the other perceived environment without any masking distance from that to the ground truth. And we can actually show that if we do the Fisher RF plus the environment masking, we're going to get a better result in terms of the closer distance from your perceived environment to the actual ground truth environment.
I have a question here.
Yes, go ahead.
So have you shown if you use if you build an uncertainty mechanism on the scene, this really helps to plan because usually uncertainty is some, for example, some details, some geometry details of the scene, it may cause some uncertainty, right? But this does not have to do with your planning.
Yes, that's true. So here we only consider, yeah, that's a very good question. So here we only consider uncertainty in terms of the position and the covariance of the point clouds, which is saying that if you have a color opacity, that is going to affect how we're going to consider the uncertainty or how we consider the risk of having the robot colliding with the environment. Thank you. And then here we show that there are also other masking techniques that you can use. You can either use a expected value, and you can either use a uniform radius. This is the goal that we want to achieve, and we argue that if we use the risk-aware environment masking, we're going to dynamically adjust based on risk values. We're going to have the highlight on the high risk areas, so we're going to ignore the low risk areas, but not like if you have a constant radius, you're going to just consider everything that's around you. All right. So to conclude, I'm going to go over time. So to conclude, for all the applications or problem that I showed, there are going to be a curve between the tractability and the gap to reality. And I show that your problem, your model can be very nicely constructed with no noise and linear dynamics, but all the way to the actual perception model that we do not have everything in the closed form. So it's similar, but the approach that we used is basically called risk aware. So we can actually solve all this kind of problem, but just keep the risk aware in mind. We can actually find the solution to the problem. It's similar to if you look at all these matrices that we have over here, and it does not look every single, but if we then take a deeper look, they will share exactly the same eigenvalues. So to conclude, the risk and awareness is actually the eigenvalues for the safe network control systems. So lastly, I would like to thank my amazing collaborator, exactly Win Bosch and Professor Daniel showed up in here, and I'm happy to answer any questions. Thank you.
Can you tell us a little more, some simpler case about I mean, you started immediately with a platoon,
Yes.
but we didn't have a clue what is the average risk you measure. I mean, can you present just the basics of it without putting it directly into the multi-agent setup?
So you mean the risk measure?
Yeah, the risk aversion.
Oh.
Measure, the risk awareness measure.
Yes.
Without going into the network control system directly, just in a basic control system.
Yeah, so the risk awareness is basically saying that how you're, of course, we don't have to be a network control system, but the risk awareness is going to give us an idea or direction how we can design or how we should design our control systems to avoid having something, avoid having a failure in current or in the future, or avoid cascading failures, say for example, in time. So the risk awareness in the very simple control system is going to be how you should plan, how you should design your feedback control such that if we can write our future states in terms of our feedback, then we can see that how your design of feedback control is going to affect our future states and its own estimation. And based on that, based on the uncertainty that we get into knowledge, the risk awareness is going to give us a sequence of safe actions, and that is the ultimate goal we're trying to achieve.
And how is it related to just robust control?
Yeah, that's a very good question. So this is going to follow a very similar path, but here we give the guarantees, or here we give guarantee in the probability risk measure, in a probability manner in terms of risk measures. It's very close, but it's not exactly the same.
And what are the other alternative measures that are used for risk?
Oh, yeah. Alternative risk measure, yes. For example, the very common one is just as simple as expected value. That is a good risk measure. The reason that we choose
Expected value collision.
Yes, that is very valid. Yes, that is a very valid risk measure, but we didn't choose it, and we choose it for the average value risk, or called conditional value risk, or CVAR, for a very good reason is that it is a coherent risk measure. And if we have a convex, so in terms of the distribution robust, when I do not have any idea of what is quantum superiority density, if we have a convex and compact ambiguity set, if we take supermode of the risk measure of all these unknown probability distributions, we're going to end up with A1. And that is a coherent risk measure which provides us convexity in terms of optimization. Any other question? Question line?
One question from Zoom. I don't know whether you can hear me.
Yes, the volume is a little bit.
We can.
Can you? Okay, great. So I'm just wondering, when you're doing the Lex best view planning, so are you doing that just for one step, or are you doing that for multi-step, like long horizon fashion?
That is a very great question. So currently we only do it for one step, but we do have a ongoing. Okay, sorry, I stopped the sharing. But I do have ongoing work with Professor Daniel's group that we're going to plan a few more steps in the future and trying to write it as an MPC problem. So currently, yes, currently it's only for one step. And then after collecting those steps, so we're going to update our ways with the collected view, then we're going to plan for the next step.
Okay, thanks. So a follow-up question regarding that is that, during your deployment, which part is more computationally expensive when you consider real-time deployment on the robot? Is that the evaluation of uncertainty and do the planning part, or is that actually the training of the NeRF part?
So currently, I think the most time-consuming part is going to computing the hashing of the hashing from the weights, which is basically trying to evaluate the information gain. But based on the
training also takes a while.
yes, that's actually true. But yes, actually, yes, that training will the 6-day iteration or training will also take a good amount of time. But computer hashing, I can see from the code that we have is they both take a noticeable amount of time, right? Currently right now.
Okay,
But
but with all that, you can still run in real time on the robots, or
not yet. That's a good question. So not yet. So currently, we, as we see over here, we have to have a pre-planned pass, which is saying that we do everything offline right now. So you do have your pre-planning, then we allow robots to collect. Allow robots to find the next best view. Then the robots will travel to there and collect. Then we'll do everything start from zero again.
Okay, thanks very much.